let us recall one-time pad, Varnam one-time pad. So in Varnam one-time pad, we have seen that your plain text space, ciphertext space, key space, all are essentially consisting of bit strings of length n. So if x equal to x1, x2, xn, this n tuple bit string, this is a plain text, and key is k1, k2, kn, then the ciphertext is generated in this way: x1 XOR k1, x2 XOR k2, xn XOR kn. And XOR means essentially this is addition modulo 2. So these are the ciphertext generation. And decryption is identical. Decryptor knows the key and decryptor knows the ciphertext. So he can simply XOR this with K1. So he can recover X1, XOR the second component of the ciphertext with K2, and he is having KX2 like that. Xn he can recover. Okay, so decryption is simple, similar to encryption. Now, why we call it one-time pad? Because if you observe, this one-time pad is vulnerable to known plain text attack. So if you know, if the adversary knows a plain text, and ciphertext is available, ciphertext is public. So if an adversary knows the plain text, non-plain text attack, adversary having access to a plain text and corresponding ciphertext also he is having. So simply XORing these two, XORing the plain text and the ciphertext component wise, he can recover the key, because this x1 XOR k1 XOR x1 will give you k1. Similarly, xn XOR kn, XORing xn will give you kn. So you can recover key. So this key, you cannot use this key more than one time. This is why it is called one-time pad. So we have seen one-time pads are essentially impractical. Why? Because n bits key is required to encrypt n bit plain text. So if your plain text is n bit, same n bit key has to be used, and each key is used only for only once, for only one encryption. Every time you have to change the key while while encrypting a message. So this is why it is called one-time pad. This key can be used only once. And as I said, this is vulnerable to vulnerable means the attacker can recover the key from if he mounts a known plain text attack. That means if you know a plain text and the corresponding ciphertext from that pair, he can recover the key. So a new key needs to be generated and communicated over a secure channel for every message that is going to be sent. So this causes a severe key management problem. So first issue is, every time this key has to be generated and sent through a secure channel. Another problem is key size. If your plain text size is n bit, the key size is also n bit. So these 3 points essentially causes a severe key management problem for one-time pad. That's why it's impractical. However, one-time pad is unconditionally secure. Unconditionally secure means what? We have two concepts. One is unconditionally secure and another is computationally secure. Means unconditionally secure means the adversary is given infinite power. There is no limitation on its how much time he can run this. Means it is given unbounded power, and crypto system is said to be unconditionally secure if it cannot be broken even with infinite computational resources. The adversary is given infinite computational resources. Okay, then also it is not it cannot be broken. Then we say it is unconditionally secure, and it can be proved one-time pad is unconditionally secure. Okay, and another one I said computationally secure means your adversary is given is a time bound. Up to this time he can run. So it is not infinite computational. It is not given an infinite computational power. Adversarial power is bounded. For computational security, the adversary's power is bounded by some time bound or some other resources. All the resources are not computational resources are not infinite. It is having limitation for getting computational security. Okay. Now, security of unconditionally secure crypto systems depends on the fact that each key is used for only one key, one encryption. So, unconditionally secure means this thing. The adversary has given infinite computational resources, access to infinite computational resources, and also we have this result due to Shannon. It says that suppose you have a crypto system consisting of plain text space key, ciphertext space C, key space K, encryption rule. This E is essentially the collection of encryption rules, and D is essentially collection of decryption rules. Okay. Now this scheme is this crypto system is such that key space size, ciphertext space size, and plain text space size all are same, like one time pad. Key space here, every key is n-bit string, every ciphertext is also n-bit string, every plain text is also n-bit string. So if you have a crypto system having this feature, plain text space, ciphertext space, and ciphertext space and key space all are same, sizes are all same, then crypto system provides perfect secrecy. It provides perfect secrecy if and only if every key is used with equal probability, one by cardinality of the key space. This is mod of k, cardinality of key space. So every key is used with equal probability, and for every x belongs to p and y belongs to, this should be c, there is a unique key. There is a unique key such that encryption of x using the key k is y. Okay, so perfect secrecy, already we have mentioned what we mean by perfect secrecy. In the next page also it is recalled again. Shannon's notion of perfect secrecy means probability of plain text given your ciphertext equal to probability of plain text for all plain text x and for all ciphertext y, where x is a plain text corresponding to x is the y is the ciphertext corresponding to plain text x. Okay, so so this theorem essentially means, suppose I have a crypto system with these conditions: key space size, ciphertext space size, plain text space size, all are same. And also, if your crypto system means your crypto system will provide perfect secrecy if this condition holds. And if this condition holds, you can show your crypto system provides perfect secrecy. This is if and only condition. Okay, so this is Shannon's theorem. It can be proved. Means if you go through Steenson, there is the proof. Okay, so you can go through that proof. Here I will not discuss that proof. So it says if you have a crypto system having this feature, then this crypto system will provide perfect secrecy provided every key is used with equal probability. That means probability of using a key is 1 by mod of k. And also each key is used only once. This is one time pad. Each key is used only once. That means for every pair of plain text and ciphertext, there exists a unique key. There exists a unique key such that y is the encryption of x under this key. Okay, this can be proved. And the converse is also true. If every key, if the probability of using a probability of using a key is 1 by mod k, every key is used with equal probability, this probability, and for every pair of plain text ciphertext, a unique key always exists, then this crypto system provides perfect secrecy. Okay, so the proof, if you are interested, you can go through the proof. It is given in Stinson. Okay. Now, Shannon's notion of this is essentially called Shannon's notion of perfect secrecy. If this condition holds, then under these circumstances, we have observed that a key is always chosen with this probability, equal probability. Every key is used with equal probability. Not only that, for every pair of plain text ciphertext, corresponding plain text ciphertext, a unique key always exists, such that encryption of x with respect to k is y. Okay, so this is why it is called, this condition is also called Shannon's notion of perfect secrecy. Now, the stream cipher, the basic strength of stream cipher essentially lies in how random the key stream is. From the key, you are generating the key stream. From the key, given key, you are generating the key stream. So, how random your key stream is. So, security of your stream cipher relies on that. So, if ki is a true random sequence, k1 from the key k, you are generating the key stream k1, k2, kn, suppose. Means so if it is not, it is going on k1, k2, infinite sequence you are generating. So if this ki sequence, this sequence is truly random sequence, then the cipher is called one-time pad. And one-time pad possesses perfect secrecy. However, this is impractical. Already we have mentioned why it is impractical. Okay, so the main objective of keys of this stream cipher is a construction is to get ki as random as possible. Now, if you have generated a key stream, how to check that it is means how much randomness it contains? So, how to measure randomness of a given sequence of key stream? So, these random numbers play an important role in the area of stream cipher. Okay. So, generally we use two criteria to validate the randomness of a sequence of numbers. First one is uniform distribution and second one is independence. Okay. So, given a key stream, uniform distribution means the frequency of occurrences of each of the members should be approximately the same. So, if you have your key stream alphabet is suppose key stream alphabet is L, and it consists of several symbols. Okay, and basic alphabet is consisting of several symbols. So, frequency of occurrences of each symbol from that alphabet in the key stream should be approximately the same. And independence, no one value in the sequence can be inferred from the other value. So, you have a long sequence, and the occurrence of this symbol here, it is independent of occurrence of this symbol here. So, there is no correlation. Okay, no one value in the sequence can be inferred from the others. Okay, so they are independent and they are also uniformly distributed. These are the basic things to validate the randomness of a sequence of numbers. So, for this we generally perform many tests to determine whether a sequence has uniform distribution. However, no test to prove independence. Okay. So, number of tests can be applied to demonstrate that a sequence does not exhibit independence. No test to prove independence, but several tests can be applied to demonstrate a sequence does not exhibit independence. So, if you have a sequence of numbers, it passes through some specific tests. We can say it is having randomness, sufficient randomness. But it is not a truly random sequence, so it is called a pseudo-random sequence. The sources of true random numbers are hard to come by. So already we have mentioned these things. Truly random number generation, random number generation, and truly random number generations is essentially it is very hard. So you have a random number generator, and whatever it generates, you can pass that sequence of numbers through several tests, and you can say, okay, I have sufficient. I have performed sufficient randomness test, and it passes through it. So it is having sufficient randomness. So we measure in this way uniform distribution. So there are several tests that it has to pass to argue that it is having sufficient randomness. So deterministic algorithmic techniques are used instead, and if the algorithm is good, the resulting sequence will pass many tests of randomness. Okay, so these are called pseudo-random number generators. These are deterministic algorithmic techniques. Okay, pseudo-random number generators. One already we have discussed, LFSR. This is a pseudo-random number generator. This is essentially these numbers are essentially bit strings. In this case, LFSR, this is binary sequence. It generates binary sequence. Pseudo-random bit generator. Okay, and this is very fast and very simple. We have already discussed, already seen. It is very simple and very efficient. Okay, hardware implementation, and generated sequence exhibits good statistical properties. If you take M sequences, that is maximum length LFSR, you choose your connection polynomial to be primitive polynomial, then so you get M sequences, and your connection polynomial is primitive polynomial. You get M sequences, and those exhibits several good properties, statistical properties. Okay, those statistical properties we are going to discuss next. Okay. Another example, this is also hardware implementation of pseudo-random number generator, actually bit generator. So this is called NFSR. This is linear feedback shift register. This is non-linear feedback shift register. So linear feedback shift register, we use a linear recurrence relation, and non-linear feedback shift register, this is having non-linear, it considers non-linear equations. So these are hardware oriented, and using this LFSR and NFSR, hardware oriented stream ciphers were designed. There are grain, this uses LFSR, also NFSR. Only using LFSR, it will not give you, this is essentially, it has linear relation, it uses linear relation. So to get a good stream cipher, linear property as well as non-linear property, both we need. Okay, so grain, this is one stream cipher that uses both LFSR and NFSR. This is hardware based. Okay, this uses LFSR, and NFSR means it is hardware based. And also there are BBM, Trivium, Mickey. There are several stream ciphers. We are not going to discuss all these things. And essentially, there was a competition launched in 2004 by NIST, and this was called eStream project. It completed in 2008, and there several candidates were finalized, and they essentially the winners were they have two portfolios. Portfolio 1 is software based stream cipher, and portfolio 2 for hardware based stream cipher. So in hardware based stream cipher portfolio 2, we have Grain 6 version, Grain 6, Mickey 2.0, Trivium, all these things. And software based HC128, Rabbit, Salsa, all these are essentially good stream ciphers that are winners in eStream project. Okay, so these are essentially anybody can use. If someone wants to use stream cipher, anybody can use this. These are open things. However, many attacks appears means when a stream cipher is designed, it has to pass through. It has to be checked whether it is whether it resists some attacks or not. So there are several attacks, that algebraic attacks, fault attack. So this algebraic attack uses Grosvenor basis, SAT solver, satisfiability problem, SAT solvers. So using those, you can mount this type of attacks and check how robust the system is. If you design your own stream cipher, you have to argue how much strong it is. Essentially, the strong how good your stream cipher is, it depends on how efficiently and how efficiently you generate your pseudorandom numbers, means bit stream, key stream. From the key, given key, how efficiently you generate the key stream, and also not only how efficiently you generate it, also you have to generate it in such a way that it contains sufficient randomness. Okay, so it is not trivial to mount this type of attacks. Or if you found this type of attacks, complexity is very high. So there are two areas people work: one designing part, and another analyzing part, cryptanalyzing part. Okay? So it is not sufficient only to design a stream cipher or block cipher. You have to also argue the existing attacks, means whether it is secure against existing known attacks. For block cipher, the attacks, differential cryptanalysis, linear cryptanalysis, those are general attacks. Block cipher, the basic attacks that block cipher should prevent. The block cipher should be secure against those attacks. And for stream cipher, we have these algebraic attacks, fault attacks, etc. Okay, this is a very rich area. Okay, very rich. Now, as I was discussing perfect secrecy, let us illustrate this with one example. So, perfect secrecy, we have say one-time pad. Means here one example, with one example I will illustrate perfect secrecy. So, one bit encryption. Suppose I consider one bit encryption. So your ciphertext bit is generated by XORing the plaintext bit and the key bit. So one bit encryption we are considering, and we are going to show that this achieves perfect secrecy under this condition. So here in this encryption, your ciphertext space, plaintext space, key space, all are same. And also each key is chosen uniformly. So your key is either 0 or 1. So probability that key is 0 is half. Probability of key 1 is also half. But suppose your probability, your plaintext is also this plaintext, P can be either 0 or 1. So probability of P equal to 0, suppose it is given 0.6, and probability of P equal to 1, it is given 0.4. So this is given. Each key is either 0 or 1. Each is used uniformly, so their probability is half. But your probability of plain text P equal to 0 is 0.6 and P equal to 1 is 0.4. Now let us show that it actually possesses perfect secrecy. So what do you mean by perfect secrecy? Again, we recall it the probability that plain text given ciphertext will be equal to probability of plain text. So you have to show your probability, your plain text can be 0 or 1, your ciphertext also can be 0 or 1. So you have to simply check whether this probability P equal to 0 given C equal to 1 equal to probability of P equal to 0 or not. So you have to calculate this conditional probability and check whether it is equal to probability of P equal to 0 or not. Okay, so your probability is given. So you can utilize Bayes theorem. You can utilize Bayes theorem, and you can calculate this value, probability of P equal to 0, C equal to 1, equal to probability, joint probability divided by probability of C equal to 1. So if you calculate this value, it is calculated here. So probability, joint probability, then you write in this way. This one you write in this conditional probability. This probability, joint probability, you can write in this way: probability of C equal to 1 given P equal to 0 into probability of P equal to 0. And then the denominator also you can write in this way. Probability of C equal to 1. So let me go through it properly. One probability. Let me explain. Okay, probability of P equal to 0, C equal to 1. This is equal to joint probability divided by probability of C equal to 1. And then this is joint probability, and probability of C equal to 1 I can write in this way: probability of P equal to 0, C equal to 1 plus probability of P equal to 1, C equal to 1. So this is the whole probability. So it is simply I can rewrite in this way: probability of C equal to 1 equal to probability of P equal to 0, C equal to 1 plus probability of P equal to 1, C equal to 1. C is 1, P can be 0, P can be 1. Okay. Now you write with backward conditional probability this way. So this joint probability can be written in this way: probability of C equal to 1 given P equal to 0 into probability of P equal to 0, and the denominator also you can write in this way. Right, in this way. Essentially we are using Bayes theorem. Okay, we are using Bayes theorem. Now what is this probability? Essentially, you know, probability of C equal to 1 given P equal to 0. When you will get that your ciphertext is 1 when P equal to 0? When your plain text is 0, given plain text is 0, you get your ciphertext to be 1 under the condition K equal to, K equal to 1. Your plain text is padded with, means your plain text is XORed with K. So P XOR K should give you C. So this should be 1. Okay. So probability of C equal to 1 given P equal to 0. This essentially same as probability of K equal to 1. Because K and P are XORed 0 and 1. If it is 0, then it should be 1. Otherwise, you cannot get 1. This way you can argue. Okay. So similarly, this one essentially K equal to 1. This probability, this conditional probability is K equal to 1, and this conditional probability, that probability C equal to 1 given P equal to 1, this you get only when K equal to 0. Okay, because plain text bit 1 and you are getting ciphertext bit 1. That means your key bit should be 0. Now you can simplify. Simply you are given this probability half, K equal to 1 half, probability of K equal to 0 is also half, the probability of P equal to 0 is 0.6 and probability of P equal to 1 is 0.4. So you can calculate this value, and this is simply probability of P equal to 0. So we have shown that probability of P equal to 0 given C equal to 1 equal to probability of P equal to 0. So you have to show this for every possible pairs P and C. So this is 0, 1. So you have to show for 0, 0, 1, 0, 1, 1. For all you have to show. Then only you can argue. So you have to show this one also. That probability of P equal to 0 given C equal to 0 equal to probability of P equal to 0. Probability of P equal to 1 given C equal to 1 equal to probability of B. So you have to check all. If all of them are this equality, this here probability part is given. Probability of this probability is, this is not scanned properly. So probability of this equal to probability of P equal to 0. Similarly, so if for all the pairs of plain text and ciphertext this condition is satisfied, then only this is having perfect secrecy. So if you consider one bit encryption, it is giving you a perfect secrecy. This instance. The probability is 0.6, probability of 1 p equal to 1 is 0.4. This is just giving you perfect sequence. If these probabilities are different also, check what you get. Same calculation, it will give you the same perfect sequence. Whatever probability you put here will give you perfect sequence. So you think if you take 2-bit encryption, so your plain text space is plain text is essentially 0001 1011. K is also 0001 1011. Ciphertext is also this. So if you consider 2-bit encryption, then and all the keys are chosen uniformly, then whether that will provide perfect secrecy. Means if you check your probability, means you will have 4 probabilities here. Probability of p equal to 00, probability of p equal to 01, 10, 11. So you give a distribution the probabilities. So all the probability sum should be, if you take the sum, it should be 1. So give the distribution according to your own preference and check whether 2-bit encryption gives you perfect secrecy or not. Okay. Okay, so next is randomness measurement. Okay, randomness measurement. So as I said, the strength of stream cipher lies in how random your key stream is. Now we are going to discuss how to measure this randomness. So randomness of a sequence, this is essentially, this is actually called unpredictable property of the sequence. This is an unpredictable property of sequence. So our goal is to measure randomness of the sequence generated by a deterministic method called a generator. So by LFSR or NFSR, I generated a random sequence. Now I have to measure the randomness of the sequences. So it is generated using a deterministic algorithm. This deterministic algorithm is called generator. LFSR is one type of generator. There are several other generators. The test is performed by taking a sample output sequence and subjecting it to various statistical tests. It has to pass through various statistical tests to determine whether the sequence possesses certain kinds of attributes that a truly random sequence would likely to exhibit. Okay, so this is the reason it is called pseudo-random sequence. It is not a truly random sequence. We are generating our random sequence using some deterministic algorithm, and it passed through several statistical tests. Okay, if it must just check whether it possesses certain kinds of attributes that a truly random sequence would be likely to exhibit. Okay, so instead of random sequence, we call this sequence a truly a pseudo-random sequence, and the generator is called a pseudo-random number generator or pseudo-random sequence generator. Pseudo-random number generator, pseudo-random sequence generator. Suppose you get a periodic sequence. So periodic sequence already we discussed. Periodic sequence means say S is S0, S1, S2. This sequence is said to be periodic if there is some positive integer n such that Si plus n equal to Si. It is repeating. Si plus n equal to Si. So this is a periodic sequence of length n. So this n is called the period of the sequence. Now let us discuss Goulomb's postulates, Goulomb's randomness postulates. This is one of the initial attempts to establish some necessary conditions for a periodic pseudo-random sequence to look random. Okay, so you have a periodic, so the Goulomb's postulates works for periodic sequence. Periodic sequence, so it's periodic pseudo-random sequence. So what are the properties it should exhibit? There are three rules, three properties. First property is, so given your periodic sequence of having period n. So every period, in every period, number of you count number of ones and number of zeros. They are almost same. They differ only by at most one. Okay, number of zeros and number of ones are almost same. So you can check this using this. So essentially, this is a bit string. Okay, I'm saying this is a bit string. So these SIs are either 0 or 1. So if you consider -1 whole to the power 0, then it is contributing 1. If it is -1 to the power 1, this is contributing -1. So if it is SI is the ith means S0, S1, S2, SI. This is your sequence. So you just raise -1 to the power ith bit, 0th bit, 1th bit, like that, ith bit. So it will if SI is 0, then it actually counts the difference between number of zeros and number of ones. So how many -1 whole to the power SI, the positions corresponding SI positions, if 0, those are added. That means those many ones you will get, and SI1, those many -1 you will get. So if number of zeros and number of, it actually calculates the difference between number of zeros and number of ones. The absolute value I have taken. So this less or equal to 1 means number of zeros and number of ones, they differ by at most 1. You get my point? So this SI, the positions corresponding this sequence, this is a bit string. The positions where it is 0, it is 0 positions, it gives you 1. So essentially 0 positions counted by this, and 1 position, corresponding 1 positions also gives you -1. So you are getting 0 positions, all for 1 0 position you get 1 1, and for one position you get -1. So all the 0 positions are added and all the non-zero positions are added, and it is giving you the difference. So it essentially counts the difference between the number of zeros and number of ones. And it says, this condition says that it must be, the number of zeros and number of ones must be almost same. It holds for every period. Within a period, it must be the case. Number of ones, number of zeros must be same. Okay, so I have an example also. Say I have generated this pseudo-random sequence 0 1 1 0. This example I have illustrated. This is generated by LFSR. Okay, this is having period 15 with cycle. Suppose S15 is 0 1 1 0. LB 4 length LFSR. I have generated this using 4 length LFSR. Now this is one period. After that it will repeat. Okay, this is periodic with period 15. So if you count number of zeros and number of ones, there are 7 zeros and 8 ones. So first condition is satisfied. Second condition, what it says, that in every period half the runs have length 1, 1/4 have length 2, 1/8 have length 3, etc. As long as the number of runs so indicated exceeds 1. Okay, so you count number of runs. Every period, half the runs have length. So length 1 runs you count, length 2 runs you count, length 3 runs you count, length 4 runs, length means you keep on doing that until you get this is half of the runs have length 1, 1/4 of the runs have length 2. So what we mean by runs, let me illustrate this with this example. So runs means same thing. So how many runs of length 1? So this is one length run. 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 Run means runs of length 1. Length 1 means single bits. 0, 1. Again, this is 0. This is 1. So length 1 means single bit. So how many runs of length 1 are there? 1, 2, 3, 4. How many runs of length 2? Length 2 means length 2 bit strings are 0, 0, 0, 1, 1, 0, 1, 1. So length 2 runs, this is 2 run, 1, 1, 1, 2. This is 3 length, right? 3 length. So 2 runs of length 2. So length 2 how many? Means how many patterns you can say. So not patterns. Patterns means length 2 runs. 1, 1, 0, 0. So two runs means consecutive 2 values are same. Consecutive 2 values are same. So we have 2 runs of length 2. Length 3. So consecutive 3 values here 3. This is 4. No, this is 3. So 1 run of length 3. Length 4. Only this one. 1 run of length 4. So if your period is total how many runs? Total how many runs? Total runs 1, 2, 3, 4, 5, 6, 7, 8. Total 8 runs I have. Runs means consecutive same value. So 0, this is 1 run. Then 1, 1. This is another run. 0, 0, another run. 1, another run. Total 8 runs I have. So it says in every period you count how many runs are there. Then it should satisfy this property. Half of the run should be of length 1, 1/4 should be of length 2, 1/8 should be of length 3, like that. So I have total 8 runs here. So half of it should be of length 1. So there are 4 runs of length 1. Then 1/4 of this should be of length 2. Runs should be length 2. 1/4 of this means 2 runs of length 2. So this is having this pattern. This is having this feature, the second rule true. Okay. Then 1/8 of this, that means 1/8 of this, that means 1 run should be of length 3. Okay. So this way it says, and as long as the number of runs so indicated exceeds 1. Okay. So 8 by 8, and after that you cannot divide it further. So when it is 1, you stop. As long as you divide it, keep on dividing it by 2 every time, first half, then 1/4, then 1 by 8, like that. You keep on dividing it until it exceeds, means till it exceeds 1. When it does not exceed 1, it is less than 1, then you stop. So in every period you count the runs, number of runs, and you count how many runs of length 1, how many runs of length 2, how many runs of length 3, so on. And the distribution of length 1 runs should be like that. Half of the run should be of length 1, 1/4 of the run should be of length 2, 1/8 of the run should be of length 3, like that, as long as you cannot divide it further. Total number of runs you cannot divide it further. Okay. And the third condition says, so this is sort of uniformity. This first condition says number of ones, number of zeros must be same. So whether whether your sequence passes through this test or not, you can easily verify by this, writing a code for this. Okay, this is your expression. Mathematically, how to check? Means whether your string having equal number of zeros, almost equal number of zeros and ones, or they differ only by at most 1. So this is the expression. You have to write a code for this. And the second condition also you can verify. You can check for every period. You count all the runs and you check whether the runs, different types of runs of length 1, runs of length 2, runs of length 3, etc. They satisfy this distribution or not. So this is also the distribution of the runs almost or satisfying this condition means it is having the feature of randomness. The third condition is autocorrelation function. Means, as I said, that in one position whatever is appearing, it is independent of the occurrence of a number in the other position. So this is called correlation. So this is autocorrelation function. It says that if you the autocorrelation function will define in this way: C tau to be -1 whole to the power Si plus Si plus tau, I from 0 to n minus 1. So what we are actually doing, you have your string, you have your sequence S0, S1, S2, Si plus 1, etc. And this I plus tau means essentially you are taking tau shift of that. Okay, tau shift of that. Let me explain with this example. So this is your initial sequence. Suppose S15 is your initial sequence. I have written it 0, 1, 1. This is your initial sequence, and tau shift. I am taking tau shift. Tau can be if tau is 0, then this is essentially same position, Si position. Tau can be 1, tau can be 2, tau can be 3, tau can be like that. Tau can be 1, 2, 3, etc. Tau can be n. Okay, tau can be n. Si plus n equal to actually Si. Okay, tau can be up to n minus 1. After that, it will repeat. So we take the position Si and its tau shift. So this is your initial. This is your S15, and suppose tau equal to 1. That means we shift it that side. Tau shift. Tau equal to 1. Tau shift. Tau equal to 1. 1 position shift. 1, 1. So 1 position shift. That means we are taking from 1, 1, 0, 0, 1, 1. So S0 position is now becoming S0 position. So S1 position is now here. Tau shift means this one is here, this one is here, this one is here, like that. Tau equal to 1 means this. Okay, so this expression actually counts number of zeros minus number of ones in this, in x minus y. So your original sequence is this given string, and tau shifted string is y. Circular shift. No, it is not circular shift. It is essentially this one. This is here. This is here. So the next part is circular shift. This part is going here essentially. This one. Okay. So in your given string x, ith position is Si. Okay, and tau shifted string we call it y, and it is essentially circular shift. Tau positions we are moving here. We are shifting this bit string tau positions, so we get y. So this value essentially calculates the number of zeros minus number of ones in x minus y. X minus y or x plus y, same, because it is bit string. It is bit string. Okay, so if you it is original string and it is tau equal to 1 shift, and you just XOR means this is Si plus 1, S0 plus 1, S1 plus 1, like that. So you calculate this. This is your x minus y, or x plus y, all same, because this is binary. And then in this value, this value, this output is essentially Si, this ith bit, this ith position, it is essentially Si plus Si plus tau, Si plus Si plus tau. Okay, so if both are 1, then it will if both are 1, it gives you 0. So if both are 1, it will give you 0. So it will, in this sum, it will contribute 1. So in this sum, it essentially gives number of zeros minus number of ones. Okay, so in this sum, if this is 0, it will contribute, this is 0, this sum is 0, means Si plus tau is 0. So if this is 0, it will contribute 1 in the sum. So it counts number of zeros. Number of zeros here. And if it is 1, this Si plus tau is 1, then it gives you minus 1. Minus 1 whole to the power. This value is 0, means this is 1. And this value is 1, means this gives you minus 1. So in the resulting sum, you are actually counting number of zeros minus number of ones. Okay. Zero values corresponding, this value 0 means this will give 1. That means all the 0 values are added up and you get number of zeros appearing in this sum, x plus y or x minus y. Modulo 2, so x minus 1, x plus y, both are same. Okay, so it says if you define the autocorrelation function in this way, shifted the given string and the tau shifted string, then it is two-valued function. More explicitly, it says C tau is n if tau is 0 modulo n. Tau is congruent to 0 modulo n. That means tau is divisible by n. And its value is t if tau is not equal to 0 modulo n. T is a constant. If tau is a multiple of the period, if tau is, it says that it is two-valued function. Either this value, this autocorrelation value is either n, the period of the sequence, or it is some fixed value t. Whatever tau you take. Okay, so tau, if it is a multiple of n, then the value is n. If it is not a multiple of n, then its value is a fixed. For all tau, which is not a multiple of n, its value is always fixed. So this type of thing should be there. So here, if you calculate tau equal to 1, so this C tau value essentially calculates number of zeros, difference between number of zeros and number of ones in the sum. Given string minus given string, sum of given string and the tau shifted string. So if you take tau equal to 1, so you count in this added value number of zeros and number of ones. So number of zeros and number of ones are respectively minus 8 and plus 7. You count 1, 2, 3, 4, 5, 6, 7. So 7 zeros you have and 8 ones you have. So if you take the difference, this is 1. So C tau value, if you calculate C tau value, this is 7 minus 8. That means minus 1. This value is minus 1. Similarly, if you take tau equal to 2 also, you can calculate this value is minus 1. So C tau, this value is always minus 1 provided this shift is not equal to the period. If it is equal to the period is 15, then the value is 15. Otherwise, it is always a fixed value. Always this value is -1. For the sequence, this value is -1. So it is a two-valued function. Two-valued function. So if it is tau you take to be n, then this si and si plus tau will be si. So this is si plus si. So it is essentially giving you 0. So it actually calculates all values here becomes 1. All values here becomes 1. Okay, so you get n many ones. So you get the value to be n. So when tau is equal to the period, or tau is a multiple of period, given period n, then you get n, value n. But if it is not a multiple of n, shift is not a multiple of n, then it is always a fixed value. So this is the most important thing in autocorrelation function. If you define in this way, then a truly random sequence must satisfy this property, this Goulomb's postulate. Third rule. Okay. So earlier we have mentioned that if you consider maximal length LFSR, LCD, maximal length LFSR means this CD is irreducible, not only irreducible, maximal length you will get only when CD is primitive polynomial. And the sequence, output sequence, whatever you get, it is a periodic sequence. It is called M sequence, and the period is 2 to the power L minus 1. Except 0, all 0 tuple, L tuple of length L. Okay, so the generated sequence is M sequence. It is a periodic sequence with period 2 to the power L minus 1, maximal period you get. And this M sequences having many interesting properties. It satisfies Goulomb's postulates, and the patterns of fixed length of at most L are uniformly distributed. This also in a theorem form we have discussed that it satisfies Goulomb's postulates, and it also satisfies this property. Every pattern, if you fix patterns of fixed length of at most L, if you consider any pattern of fixed length of at most L, they are almost uniformly distributed. So these are source of random sequences. These LFSR generated sequences are source of periodic pseudo-random sequences. Okay, so it's almost 57 minutes. Just let me complete it. Okay, let me complete it. So there are five basic tests. Already we have discussed to measure the randomness of a sequence. It must pass through the Goulomb's test. The three rules stated in Goulomb's test should be satisfied by the should be exhibited by the generated sequence. So that Goulomb's postulates are for periodic pseudo-random sequences. There are other statistical tests. There are 5 basic tests to measure pseudo-random sequence generator, the bit string generator. Okay? First one is frequency test. Whether the number of zeros and number of ones in the sequence S are approximately the same as would be expected for a random sequence. This is essentially the rule 1 of Goulomb's postulates. This is mono-bit test. Okay, frequency test or mono-bit test. Number of zeros, number of ones, approximately same. How to measure that also in Goulomb's test we have formulated using mathematically how to formulate that we have exhibited. Another is serial test. What is serial test? This is 2-bit test to determine whether the number of 00, 01, 10, 11 as subsequences of S are approximately the same as would be expected for a random sequence. So these are essentially runs. So determine whether the number. So these are the runs of length 2. So runs of 0, 0, you find the zeros. How many 0, zeros are there? How many 0, 1s are there? How many 1, zeros are there? How many 1, 1 patterns are there? And all these patterns should be approximately the same. As a subsequence of S, they are approximately the same as a truly random sequence is expected to exhibit. Rounds test, this is also in the second postulate of Goulam's. We have stated to determine whether the number of runs of various lengths in the sequence satisfy the condition R2 rule 2 as expected. Rule 2 stated in Goulam's postulates as expected for a random sequence. So first one is monobit test, second one is serial test, 2-bit test, Ran's test. Poker test, it says that suppose m be any positive integer. Now divide the sequence. So you have the sequence you have the sequence of length n, suppose, and you divide it into n over m non-overlapping parts of length n. Okay, non-overlapping parts of length n. Total n length string, and you divide it into parts, non-overlapping parts of length m. These many non-overlapping parts. So total n length string. So n means m length blocks. You divide it into lengths of m blocks, non-overlapping. So how many blocks you will get? N by m many non-overlapping blocks you will get. Now to test whether the number of each sequence of length m are approximately the same as would be expected for a random sequence. Okay, so each m length string, you have the total. You are considering the total string of length s. You divide it into a non-overlapping strings of length m each, and each m length string will give you a pattern, and you check whether that pattern, this number of a particular pattern, you pick one block of length m, and you check whether the sequence of length m are approximately the same. Each sequence, occurrence of each sequence in the string is approximately same. Okay, so uniformly distributed or not. An autocorrelation test, this is the third rule stated in Goulam's postulates to check whether correlation between the sequence and the shifted version of it approximately 0, when the number of shifts is not divisible by the period as expected by a random sequence. Okay, so these are the 5 basic tests, and if a sequence bit string to be random sequence, it has to pass through these tests, basic tests, and all the statistical tests have a way to, which there are tools to test. Okay, so if you go through this book, Handbook of Applied Cryptography by Meneges, Orscott, Manstone, this basic test, these Goulam's postulates, all are taken from that book. Okay, so soft copy version also available. Check that. As I mentioned, just this is my last page. So to check the frequency test, this parameter is used. This x1 is used. X1 is n0 minus n1 whole square divided by n. So n0 is the number of given sequence. In your given sequence, you count the number of zeros. This is n0, and n1 is the number of ones in S. So this random variable must satisfy chi-square distribution with 1 degree of freedom if n is greater or equal to 10. So frequency test, for frequency test, this is the tool used. Okay, so you can use this statistical tool, or you can use that expression in the rule 1 of Goulam's test. Okay, so this is another way of checking whether your sequence is a sequence passes through frequency test or not. So this variable, this random variable, if you define the random variable in this way, n is the total length of the string, n0 is the total number of zeros, n1 total number of ones. So this n0 minus n1 whole square divided by n, this should have chi-square distribution with 1 degree of freedom. For serial test, we use this x2 variable. So what is this? You count the number of 0, 0, occurrence of 0, 0 in S, number of occurrence of 0, 1, 1, 0, 1, 1. You name them n0, 0, n0, 1, n1, 0, n1, 1. And you take this random variable as your rule. Okay, so x2, if you define x2 to be 4 by n minus 1 into n00 square plus n01 square, n10 square plus n11 square minus 2 over n0 square plus n1 square plus 1. Then serial test, it passes to serial test means this random variable should satisfy chi-square distribution with 2 degrees of freedom. If n is greater or equal, there is some bound on n, restriction on n. It is for frequency test, n should be greater or equal to 10. For some lower value, it may not satisfy this chi-square distribution, lower value of n. Okay, for n greater or equal to n, it must satisfy this. For serial test, for n greater or equal to 21, it must, this parameter, this random variable must satisfy chi-square distribution with 2 degrees of freedom. For poker test also, this type of statistics can be used, that approximately follow chi-square distribution with 2 to the power m minus 1 degrees of freedom. Their statistics used is this one, this expression. So this whole string of length n is divided into blocks of size m each, non-overlapping blocks. So we have n by m many such blocks. So this is the statistics used. Okay, 2 to the power m by k summation I equal to 1 to 2 to the power m ni square minus k, where ni is number of occurrences of ith type of sequence. So ith type, this m length bit string will give a pattern. So how many times this pattern comes? So that is your ni, number of occurrences of ith type of sequence of length n. So you name them. This is first type, this is another second type, like that. So ith type sequence of length m. If ni is the count, then this statistics is used. And this is essentially, if you take m equal to 1, it is frequency test. So this is more general. And poker test, this random variable should satisfy chi-square distribution with this degrees of freedom. Okay. For rounds test also, statistics is used. Some statistics you can use that follows chi-square distribution with twice m minus 2 degrees of freedom. Autocorrelation test also satisfies the statistics used that approximately follow normal distribution, normal 0, 1 distribution. So if you want to learn more, you can go through the handbook of cryptography, this book. Okay, so all these things are taken from there. Okay, so these statistics, these two statistics I have not written here. Means what random variable, what is the random variable you should define? This x3, this is suppose x4, this is x5. So what are those? You can get it from that book. Okay. So let us stop here. Let us stop here.